All right, good morning, everybody. Pretty sparse crowd in person today. That's all right. Today we're going to be talking about rivers and flooding, flooding as a hazard. And in order to understand that, we need to understand how river systems work, their dynamics, the dynamics of the water cycle, and not just the three components of evaporation, condensation, and precipitation. There's even a lot more that goes into it. So we're going to talk a little bit about that. We're also going to talk about flooding as a hazard. Flooding is probably the most common hazard that most people around the world experience. Not everybody lives near earthquake-prone areas, but most people live near water because water is a necessity for human life. So most people in societies have lived near water for a long time. So we're going to start by explaining river systems like the San Lorenzo watershed. You guys have probably heard the term watershed. You may know a little bit about it, so we're going to go into greater detail about what constitutes a watershed, and we're going to talk about those different systems. Here. Okay, so we all know the hydrologic cycle: evaporation, condensation, precipitation. But there's a couple of more components that go into this. So let's say if we start with a drop of water on the land, it can evaporate into the air. It can be soaked into the soil through infiltration. It can flow as surface runoff into a larger body of water. It can then enter the groundwater by infiltration. If it flows into, or if it's absorbed by a plant, those plants transpire. They have these little cells on their leaves called stomata that open up and release water vapor. So that's another way that it can enter into the atmosphere. It can be stored in large cloud systems. It's not going to be rained out until it reaches a certain weight. So these can be stored in a lot of different areas. So whenever we're talking about the hydrologic cycle, what we're really talking about is where is it being stored, where is it being transported, and how is it being moved from those different areas of storage. So we're going to be using the term storage a lot. We're going to be using the term reservoir a lot as well. So this is what Earth's water looks like. 97% of it is in oceans. So that means it's ocean water. It's unusable by humans. We can't drink it, obviously. Anybody that's drank a lot of salt water at the beach can tell you that it's not fun and it doesn't taste great. Also, it's super bad for you. If you drink a lot of salt water, you may have to go to the hospital. Happened to my brother once, actually. He had just drank a bunch of salt water at the beach one day and he had to get his stomach pumped because he's an idiot, but what can you do? So out of all the water on Earth, 2.8% of it is fresh water. That's what we can use. Now, of that 2.8%, about 2.15% is locked up in glaciers. We can't really use that water until it melts. It's locked up in these large ice sheets. Another 0.62% of that is groundwater. Groundwater we can use, but we have to pump it. We have to drill down to it and pump it out from the deeper parts of the earth. So then we get to the even smaller percent that you can't even see there. Freshwater lakes, saline lakes, and inland seas like the Black Sea, Caspian Sea, Salt Lake in Utah, Great Salt Lake. That's also a saline lake. Soil moisture in the atmosphere, that also accounts for water that we're measuring here, but just 0.001% of all of the fresh water on Earth is in stream channels. And that's such a small percent, but it defines the entire surface of the Earth. Most of life lives near stream channels. Everyone has seen a stream before. And stream channels form the different geomorphic features on planet Earth. So even though it's such a small percent of the water on Earth, it's created such a unique and different surface on the planet that we live, which is pretty crazy. So the number one thing that rivers are controlled by, number one is gravity, obviously. As you know, water flows uphill to downhill. So it will always flow downhill. You will never have a river flow uphill. Real basic rule of thumb of science. Gravity is number one when it comes to forces. So for example, this is the Green River in the Wind River Range of Wyoming. It starts at 8,000 feet above sea level, high up in the mountains. Has a very steep gradient, so that's where we get these beautiful waterfalls, that crisp, clean water, incising the rock. And at this picture to the right, that's at Split Rock, same exact river, Green River, but we're at 4,800 feet above mean sea level. We don't have those big, beautiful waterfalls anymore. We have a much gentler slope, but we have a lot more water, as you can see. So we've built up and captured a lot more tributaries. Second one is politics. This is the Hoover Dam. Oh, sorry, no, that's not Hoover, that's Glen Canyon Dam. Hoover Dam is up a little more in Nevada. But both are on the Colorado River. Colorado River is one of the biggest river systems in the United States. It supplies a lot of water to the surrounding desert states, Utah, Arizona, New Mexico, Colorado, of course. And it captures a lot of water from those four states. So because it captures so much water, we use that for hydroelectricity. With big projects during the New Deal, right after the Great Depression, was building hydroelectric dams and generating power, just because rivers have so much force behind them that you can generate a lot of electricity from them. What happens when you dam up a river, though, is everything downstream kind of gets screwed over. So as you can imagine, the Colorado River eventually flows into Mexico. So we have to have a treaty with Mexico to ensure that they get a certain amount of water from the Colorado River and we don't block all of it. That'd kind of be a dick move. So that's the same case as we have with the Delaware River. Pennsylvania and New York have certain restrictions on how much water they can extract from the Delaware River watershed to ensure that the states more downhill and downstream can still get access to that water as well. So water is, as you can imagine, super important resource. A lot of political and engineering goes into mapping out, delineating, and establishing definitions for water usage and water in general. So a stream is a body of water that flows downslope through a clearly defined channel. This is not only just a scientific term, this is a legal term. So environmental lawyers, lawyers of water companies, representatives of state houses and congressional districts use this term for legalese. It helps define how we delineate these bodies of water, what counts as a stream, what doesn't count as a stream, and how we can protect them. So how do streams form? Basically, all that water that gets pushed onto the land surface from gravity, it sits at a certain water table, and then at some point it finds a slope and is continuing down a certain slope, incising the channel, and that's how you get the development of a stream channel. So important thing to remember is the water table. Whenever we talk about water table, that's where we're talking about groundwater. There's a point at which you can drill into the earth at a certain depth, and you're going to hit groundwater. That's the water table. Certain streams have their channel lower than the water table, so that's known as a permastream, where it's usually fed by groundwater and not just from surface water runoff. So we have this equation that we use, a real basic equation that can be applied to any stream channel that you want. So you have the volume of precipitation that gets to the stream on one side. Now you have on the other side runoff, which is water that runs over the land surface. Infiltration, water that gets into the soil and infiltrates the soil. Interception, that's stuff that's catching the water that falls from precipitation, like plants or say impervious surfaces like parking lots, houses, stuff like that. Evaporation, of course, don't need to explain that one. That's where it evaporates, turns into water vapor as a gas and rises into the atmosphere. So basically, this is what is an equation of storage. How much water you have on one side versus how much water you have on the other should be equal. So you have your input on one side with the volume of precipitation, your output on the other, and those should add up to the same number, or relatively close at least. So for evaporation, we know as you heat up water, it evaporates, turns into a gas, and that gaseous water goes up into the atmosphere. We can also have what's known as sublimation. Sublimation is where you go from a solid directly to a gas, rather than melting first into a liquid and then turning into a gas. You go directly from solid to gas. Also, we mentioned when we were talking about volcanoes, a lot of volatiles in those volcanoes. The biggest one, water vapor. So that's a source of water as well. So if we have volcanic steam, like the geysers in Yellowstone and that caldera there, that counts as part of the water cycle as well. It probably hasn't seen a stream for a while, but eventually it's going to end up in a stream. So plants are also very important. We mentioned transpiration. That's where water is brought in through the root systems, and that water can be from groundwater, it can be from infiltrated water that's come from the surface. But eventually, after that water has been used by the plant, it's going to transpire. It's basically a plant's version of sweating. They're going to release some of that moisture out through those plant stomata. So this is basically the evolution of a stream. So at the top, we just have what's known as sheet wash. Sheet wash is what you see out on the street today. All of that water just kind of moving along the surface, no defined channel at all. It's just flowing on top of a surface. Once we keep using, as we continue to sheet wash over more and more periods of rain, we're going to start to incise into the surface of the earth itself. That's where we're starting to get a channel. So we have sheet wash going into a channel, we're almost there, and then we finally get to proper defined channels here at the bottom, where we have tributaries, well-defined tributaries. So all that water is being caught in those surfaces between them. We flow into those tributaries, and those tributaries feed into the main channel that you see at the bottom. Let's skip this. Okay. So as I said, the definition of a stream isn't just a scientific term, it's a legal term, and it's a binding legal term. So if there's a stream or body of water in the area that we think is a stream, that stream is, I don't want to say has rights, because obviously it's not a human thing, but it has legal protections that need to be put in place, because streams are where we get all of our water. If we have some type of, let's say we want to build a mine. So this is from northeastern PA. If any of you are familiar with the area of Hazleton, there's a lot of coal in that area. That's Carbon County. So if they want to dig coal up from this, the top of this hilltop, they need to think about where those mine tailings are going to end up. So if there's a stream nearby and it's defined as a stream, that stream is enabled for protection. And then that mining company has to take into account whatever mining that they do, if anything will happen to the stream nearby. If it's not a stream and it's not defined as a stream, they don't have to worry about it as much. They just have to do whatever it is to protect proper water sources that are defined nearby. So we mentioned the term watershed. Watershed is another term for a drainage basin. Basically, you have a certain defined area that flows into a certain defined waterway. So for example, you've probably heard of the Chesapeake Bay watershed. It's one of the closest ones. It's one of the biggest ones in the East Coast, and it's entitled to a lot of protections. As you can see, it covers a huge area from Virginia all the way to New York. So all of that shaded blue in that area is, if you think of a single droplet of water that falls from the sky, if it falls within that blue area, it's going to eventually flow out to the Chesapeake Bay, anywhere you choose in that blue area. If it's outside the blue area, it's going to flow into a different watershed. Watersheds have definite boundaries, and based on where that water droplet falls, it's going to end up in a completely different place. Now, if let's say we have a water droplet fall all the way up in New York and a water droplet fall in, let's say, Baltimore, they're going to reach the Chesapeake Bay at different times, obviously. One might be sooner than the other, as you can imagine, but they're both going to end up at the same exact place eventually. They're both going to end up in the Chesapeake Bay, no matter where they fall in that watershed. So we also use the term catchment because it's catching the water that falls from the sky. And we have different ways of organizing these stream catchments based on order of magnitude of the stream channel itself. So if we have a single tributary, that's considered a first order stream. That means nothing else flows into it except surface runoff and groundwater. That's the only thing feeding those streams. So those are in the red there at the top. Now, a second order stream, that's where we have two first order streams coming in to form their own larger channel. So a second order stream has two first order streams coming into them. A third order stream has to have two second order streams coming into it. And so on and so forth. Fourth order streams have to have at least two third order streams coming into it. So if we have a fourth order stream, all we care about is the next lower order of stream magnitude. So this is how we establish the size of a watershed. This is how we map out watersheds as well. So it really helps us define a catchment area. All right, so I know it's a little hard to see, but based on this map, is Newark, where we are right now, is any of the rain that's coming down outside going to end up in the Chesapeake Bay? Yes or no? You can just shout it out or shake your head. No. Why is that? It's in the Delaware River watershed. Very good. So we're on the other side of that Chesapeake Bay watershed. All the water that comes down here outside is going to flow into the Delaware River and eventually Delaware Bay. So that's where our water falls. Now, the reason for that mainly is because of topography. So if you think of where we are in Newark, we're in the only area in Delaware where there's a lot of hills. So those hills define this boundary between this portion of the Chesapeake Bay watershed on one side of the hills and the Delaware Bay watershed on the other side of the hills. So since we're on the other side of the hills, all that water is going to flow into the Delaware Bay rather than the Chesapeake Bay. So topography is going to be really important here. So, and that's what we call drainage divides. It's these ridges, these higher elevations that divide different watersheds. So as we know, water only flows downhill. It's not going to flow uphill. Even in the subsurface, even when we have groundwater, it's still going to flow downhill. Gravity still exists underneath the surface of the earth. So all of that water is going to flow downhill to the nearest tributary downhill, even though it may be closer to another tributary on the other side. So we have a bunch of large-scale divides in the United States. These define huge watershed areas. So if we have, for example, this is Triple Divide in Montana, no, not that one, sorry. Montana is over there. Triple Divide Peak in Montana, there's this, also known as the Hill of Three Waters. It's this peak where each slope of this peak separates into a completely different watershed. So just a difference of a few feet, falling on a few feet in that boundary can be the difference of flowing out to the Gulf of Mexico, to the Pacific Ocean, or to Hudson Bay. Completely different watersheds, completely different areas, all from the same peak, which is pretty crazy. So as you can imagine, our biggest watershed is the Mississippi River. The Mississippi River is huge at itself. And in order for the Mississippi River to be so large, it has to catch a lot of water from a very large area. So most rivers are, their size is based on the area of catchment. If you can catch more water over a larger area, then you're going to develop a much larger stream channel. That just makes sense, doesn't it? But we can also divide these up into smaller subregions. So we have the Missouri River, the Upper Mississippi, the Ohio River ends up flowing into the Mississippi. We have the Tennessee watershed, the Lower Mississippi, and the Arkansas Red-White River watershed. All of these add up and into the whole Mississippi River drainage basin. So we've been talking about watersheds for a long time in public policy, mainly because, as you can imagine, as streams flow downhill in a watershed, it's going to pick up anything that is in its way. And that can include trash, litter, contaminants. If it's flowing into a plume of a gas leak or something, it's going to carry it with it. So anytime you care about what goes into the ocean, you have to think about everything upstream. So most watersheds have their own environmental programs put in place to protect the watershed itself, to monitor stuff that comes out of the watershed, and that helps us kind of track down where contaminants could possibly be. So if you can imagine the Chesapeake Bay watershed, there's a huge environmental monitoring program involved in the Chesapeake Bay program. Even as far as I got my undergrad at Shippensburg University, a university you've probably never heard of. It's in Bumfuck, Pennsylvania. It is just a small university, but we had even had environmental monitoring devices in Chesapeake Bay because Shippensburg is situated in the watershed. So anything that we input is going to end up in the Chesapeake Bay. So we have a say in the monitoring. We're able to get our own devices out there, do our own science. That helps to educate a lot of people that are, as you can imagine, Central PA is pretty disconnected from the ocean. So it helps us get our students to learn a little bit more about coastal science, coastal environmental policy, stuff like that. So it's a really good opportunity. So because watersheds are so large, they're also incredibly complex. So this is everything that goes into a river basin. I should have used a lot bigger font, clearly, but you have agricultural practices, air and surface temp, riparian vegetation. Riparian is just the vegetation along the borders of a stream channel, helps keep the stream channel defined, keeps the temperatures low, keeps it healthy. We have sediment transport, huge in river basins. Soil types, how much of the landscape gets eroded, and these are all interconnected to themselves. So if we have more a change in water storage, if we have some snow melt, some precipitation, that's going to impact the flow. If we impact the flow, we're going to impact water quality. We're going to impact sediment transport. We're going to transport more sediment. We're going to change the type of aquatic biodiversity. If we have more water, we're going to have a deeper channel. That's going to enable more larger aquatic life to live there. Same thing as if we decrease our precipitation, if we decrease the amount of water in the system, We're going to decrease the flow. We're going to transport less sediment. We're going to feed less vegetation. Smaller aquatic life is going to prefer this area rather than larger aquatic life. We're also going to change the water quality. If we have too much stuff in there, we're going to impact the oxygen exchange and what can live there and what can't. So these are all interconnected and interwoven. So it's an incredibly, incredibly complex system that goes on in a watershed. So basically what we're trying to do as scientists, as public policy makers, is to try to reach a state of equilibrium where any feedback we get is equal to the input. Input and output want to stay in the same loop. So we want to make sure that we have balance. Okay, so why do streams take the paths they do? So this is an example of, this is up in upper New York. We have Lake Placid, which you've probably heard of from a really old horror movie. We have All Stables, New York, all the way downstream. This flows up to the north, and that eventually will end up flowing into Lake Champlain. So we have a higher elevation at Lake Placid, and we have a lower elevation at All Stable Forks. So as we've mentioned, it only flows from uphill to downhill, even if conversely, a lot of people, whenever they're first studying streams and they're looking at maps of streams, they don't understand why, for example, the Nile River flows north. North does not mean up. North just means north. It's not uphill. So streams always flow downhill, no matter the elevation. Okay, so this is a stream profile, and we make these frequently because this helps us figure out points of erosion, points of transport, points of deposition. So if we were to stand in the stream channel and we were to walk along the entire stream channel, this is the shape that we would get when it comes to our elevation. If we took a GPS measurement at every point along that, this is the shape that we would get if we graphed those points out. So as you increase in your distance to downstream, you're going to decrease in elevation on some exponential curve. Sometimes they have different shapes, but usually it's this general shape. So this is point A, where we have the headwaters, upstream portion. This is point B, the outflow. As you can see, we have the lowest elevation, the gentlest slope, compared to A, where we have the steepest slope, highest elevation. So as we said, the profile is the steepest at the higher elevation. We have the highest gradient. Gradient is just another word for slope. We have a steeper slope we're going to have at the higher elevations. Conversely, the profile is going to be the shallowest and have the lowest gradient, lowest slope at the mouth of the river, the base level. We're closest to the ocean, the closest to sea level. So we're going to have the lowest elevation at those points. So just keep in mind, just refresh your memory, gradient, another word for slope. Slope is just rise over run. Your elevation over the distance you've traveled. And that's an equation. Your elevation, that's a number in feet, divided by distance, that's a number in feet as well. Can also be measured in any other way, but you're going to be using the same units. So gradient is a unitless number. If you're dividing feet over feet, you get nothing. So it's just a number that you get for gradient or slope. Okay. So what is the gradient of the Colorado River between Lee's Ferry at 3,100 feet and Boulder Canyon at 700 feet? So the distance between those two is 350 miles. So go ahead and calculate that gradient for me. We have a distance of 350 miles and that elevation difference. Tell me what you get in feet per mile. Okay. Yeah. B, 6.9. That's exactly right. So how did you calculate that? That's exactly right. Well done. So we have two different points of elevation. Remember, we want the change in elevation. So we want the difference between the two, 3,100 minus 700. Now we have our rise over our run. Our rise is that top portion, 3,100 minus 700. Our run is going to be the distance between the two, 350 miles. Now, in most situations, we're going to be using the same units. So rather than it being in miles, we would use feet. So that's how we get our unitless number. But in this case, just to keep the math easy, we chose feet per mile. So very good. So another thing that gradient controls is not just the longitudinal profile, but also the shape of the stream channel. So up here at A, we're going to have a more V-type shape for the river channel. We're going to be incising into the earth a lot more. Because we have a steeper gradient, we're going to be cutting into the earth. This is the area of erosion, of weathering, of breaking apart the rock. Once we get down to site B, we're going to get a wider stream channel shape. We're not going to be incising as much. There's still a little bit of incision, but this is the area of deposition. This is where all the stuff taken from the headwaters is transported down and deposited into those lower elevations. So because we have a lower gradient, we have less energy. We're not going to incise as much. We're going to drop everything out of suspension, which we'll talk about in a bit. So steep gradient, steep channel walls. Gentle gradient, shallow channel walls. Good thing to keep in mind. All right, so we have three different zones whenever we're talking about river systems. So we have the first zone, zone 1 is going to be an erosional zone. This is where we're incising, where we have those steep gradients. We're going to be breaking apart rock. Then we're going to have our zone of transport in this area where we're transporting those erodive materials, all that sediment that we break down, and we can deposit them on point bars. We can take them away from point bars. We'll incise the cut banks, and we're just going to keep moving and moving all of this stuff. And then eventually, we're going to get to the zone of deposition, where we're finally just going to drop all of that sediment, all of that material that we've carried from the headwaters. We're just going to drop it out of the river system right at the delta of a river. That's why deltas are so fertile. They carry all that soil from the headlands. That's why a lot of people farm in those areas as well. Got a lot of really nice soil. All right, so let's talk about zone 1. So we have erosion at these zones because we have a steeper topography. We have a lot more precipitation. Because we have that steep gradient, the water is moving a lot faster. If you have a steeper hill and you're on your bike, you're going to roll down that hill a lot faster than you would if you were just out here on College Avenue. So the water velocity is going to be a lot faster, and that's going to enable us to downcut and incise into the rock, into the soil, whatever the stream channel is built upon. So that's why we have so much erosion at these areas. So all that erosion takes a lot of energy. If we have a steep gradient, we're going to increase the amount of gravitational force on that water. More gravitational force, more energy, more erosion. So think of whitewater rafting versus just inner tubing down the Delaware. Very different energy compared to the both of them. So because we have that steep energy, because we have that high energy, we're going to get those steep incised V-shaped channels in those river valleys up at the headwaters. We're going to keep it a very narrow stream. It's not going to be wide. If you think of the mouth of the Mississippi River, it's almost it's hundreds of meters across. Versus if you go up into upper Missouri, we're gonna have much, much smaller stream channels, very narrow. So how do rivers erode? So they erode in 4 different ways. We have hydraulic action, which is the actual movement of the water itself. It's forcing itself into cracks, and that force is just gonna widen them, push them open, and break them apart. Abrasion, since water is a fluid, it doesn't have a lot of friction behind it, but it can carry a lot of other materials that can abrade. So you have rocks and stones that are being carried along with the current. They're going to bounce off of and break apart, creating new rocks and breaking them down into smaller rocks. It's also going to drag all of that sediment on the channel floor. That's going to create a lot of friction, a lot of abrasion. It's going to break apart that channel floor. Attrition is just the rocks and stones that are being carried, just bashing into each other. Those will eventually break those down. And then solution. So if we have, all water has different chemical properties based on where it's originating from. It may have, say, a little more carbonic acid in it, may have, be a little more alkali. It can break down those rocks chemically and transport them in solution. So we get a lot of that in Pennsylvania because we have a lot of limestone. Limestone reacts with hydrochloric acid very, very readily. It's one of the ways pretty much every geologist carries a vial of HCl in his bag, just because to tell the difference between limestone and most other rocks, you just drop it on and it fizzes. It's a really violent reaction. So same thing happens with acid rain. If you get all that acid rain precipitation into a watershed, you're going to break down that limestone chemically rather than just through a hydraulic action. So that's going to help break apart the rocks as well. That's how we're going to erode them. Okay. So whenever we're talking about streams, a really important thing that we're talking about is the load that it can carry. So that's basically determined by different types of sediment. So we're going to talk about the different sizes of sediment. So we have 3 different types of load. We have the bed load, which is the sand, the gravel, real heavy stuff, bigger stuff. You can see it. You can see it with your naked eye. You can see the different grain sizes. It's about 10% of the mass, so not a lot, but significant enough that we want to calculate it. We have our suspended load, that's clay and silt particles, real small, real fine grained. If it was turned into a rock, you couldn't see the differences in any of the grain sizes. You couldn't see them at all. So suspended load, it's going to be carried in the actual current. Now we have our dissolved load, which is the soluble stuff. That's stuff that we've dissolved through our chemical means. This can be from minerals like limestone. It can also be from pollutants as well. So that's going to be carried in solution. So that total, all of this added together is the entire stream's capacity. How much can the stream carry before it stops being a stream? As you can imagine, if we have so much sediment that the amount of sediment is greater than the amount of water, we're not going to move that sediment anywhere. So it ceases to be a stream at that point. So it's all about how much can it move before we've reached the total capacity of motion. All right, so this is up in Alaska. These are these headwaters in Alaska. This is part of the bed load. We can see these grains clearly. So we have our sand, our gravel, those larger stones right there, probably cobble sized. So they're sliding, they're rolling, and they're moving away. And they're being eroded from the channel, the bottom of the channel, even though this is a very small channel, small tributary. We're up much higher in the head levels. So you can almost see the stream channel getting deeper and deeper at the center of it. Okay, so is this going to be a zone 1, 2, or 3 stream? Remember, zone 1 is erosional, zone 2 is transport, zone 3 is deposition. 1, 2, or 3? You can just shout it out. 1. We have one vote for 1. Anyone else? 2, 2, 1. It's 1. So even though we're moving this stuff away, we still have so much energy that we're eroding more of it. So in transport zones, we have the movement of stuff, but we also have a little bit of deposition. So it's like that intermediate zone between the erosional and the transport zone. So this is going to be a zone 1 because all we're doing is eroding it away. The difference between erosion and deposition? Okay. Deposition is where we have stuff that's in motion. We're getting to a low energy environment. All that sediment is going to fall out and it's going to stop moving. So that's where we have deposition. It's being deposited. So if we think of a deposit of something, we're talking about something that was taken from one place and put in another, and that's where it stayed. So that's deposition. Erosion is the actual breaking away and the physical breaking up of these materials. So that's the removal of where it originally was. So you can have stuff that was deposited long ago, and then you can erode those materials away. Does that make a little more sense?
Yeah, so basically, erosion is the beginning of the process.
Exactly. Very good. Okay. So now we're getting into suspended load. This is the largest portion of the load. Now it's hard to see with this video, but you can see how cloudy the water is. This is done in a lab, so the water they're using is tap water. You should be able to see through it. Because it's so muddy, all of that stuff, all of that mass at the top is the suspended load. All the clay and silt particles, they're carried by the flowing water. Because they're so small, they're going to stay in suspension for longer periods of time. They can be transported a lot further than those heavier rocks that you see bouncing on the bottom of the surface. So this makes up the largest amount of the flow. Because we need so much more energy to transport larger rocks, and we need a lot lower energy to transport the suspended load, that's why the suspended load is the largest portion of the total load. It can be transported by the smallest streams that we have, as well as the largest rivers that we have in the country. And then we have the dissolved load. Even though we have a muddy water, we couldn't even see the dissolved load if there was no motion whatsoever. So this is where we're talking about ions, just molecules of stuff that have been dissolved and placed into the water currents, and they're transporting that way. This makes up still a pretty small portion, just because it's also hard to sample because it's so small. And if you get just a water sample, say the size of a bucket, what is that bucket compared to the rest of the Mississippi River? So it's a very, very small component, but it's still important enough because those ions could eventually form into new molecules, deposit elsewhere, and we can map out those deposits. But this image is actually pretty good for describing the different movements of bed load. So we have all these larger cobbles and gravels on the bottom of the channel, and they're going to move in different ways. So we have what's known as traction. Traction is another word for rolling, where all those boulders, they're using basically Bernoulli's lift, all of that force from that current flowing over top of that rounded grain. It's going to end up rolling it all the way down. And since we're always flowing downhill, stream channels have some slight slope to them. So that's going to help us as well. Gravity is going to help us as well. We have what's known as saltation. Saltation is a confusing word. It has nothing to do with salt, nothing to do with it at all. I cannot stress that enough. That is one of the questions that I always got wrong in Intro to Geology when I was just starting out as a geologist. Always got it wrong. Saltation is where instead of just rolling, we're going to start bouncing. So it has so much momentum that it's just going to bounce on the floor of the channel. It's going to help break apart some of those rocks through abrasion, through attrition. They're going to smash into each other. This is where we have saltation, where we have a jump rather than a roll. Suspension, obviously, is the stuff that we're seeing muddying the water, the real small stuff that's up into the current. It's not interacting with the bed at all. So that's the suspension. And then obviously solution is going to be the dissolved stuff, the dissolved ions. Okay, so now we're getting into zone 2, the transport zone. This is where we have river bars, floodplains. This is where most of human civilizations that live along rivers live. They don't live near the headwaters. A couple people live near the headwaters, of course, but most people live near these floodplains and these river bars. And there's a good reason for that we'll get into. But now we're getting into a little bit lower energy. We're not so steep of a gradient that we're going to still erode something, but we're also going to start depositing stuff. We have such a low gradient that we can develop a bit wider. And in order to maintain that energy, we're going to develop a lot of meanders. So we're going to talk about each of these in turn. So I wanted to play this video mainly for this right here, just to show how meanders change. Okay, so I'm going to post that video on the Canvas site because that'll be helpful to see how the meanders develop. So as we've seen, all of these back and forth motions will eventually create a meandering stream. And because we don't have that steep gradient, it's a lot easier to develop meanders. You're not going to see a meandering stream in the high mountains just because the gradient's so steep, it just wants to flow downhill. Whereas on a more gentle plain, you have the room, you don't have all these hard rocks that they have to incise into. All they're incising into is soil. So it makes it a lot easier to develop all of these meanders. So this is a time lapse of the Amazon. And you can see that these meanders, they're going to change over a relatively short amount of time. So this is over, I think, 10 years that these meanders have changed. So if you look, eventually a meander will get so great that it will merge and it will just jump over and shorten the entire length of the channel. So that feature where we have this gigantic meander that eventually gets cut off, that's called an oxbow. So we have oxbow lakes that are just former stream channels that are in this like bow shaped that get cut off because it's so much easier for the water to travel this distance than it is to follow the entire meander. So yeah.
Do areas in South Carolina, Georgia, Florida, do they have similar?
Yeah. So that's on South Carolina, Florida. That's part of the coastal plain. So we're far away from the mountains, so we're going to get a lot of meanders like this. The only thing that would prevent these from forming is human engineering. So we probably have less meanders on the East Coast just because we've developed the East Coast so much. But definitely south of the Carolinas and Florida, you're going to get a lot of stream meanders for sure, definitely. If any of you are familiar with fishing in the area, there's a lot for sure. In fact, the Everglades have a lot of meanders running through them as well. All right, so just like we saw in this video, velocity of the stream channel is going to define where we get a stream meander. So in a regular channel, let's say this was made of concrete. We just have a regular bowl-shaped concrete channel. Velocity is going to be fastest right in the center. Mainly, the main reason due to that is because we have friction along the sides of the channel and on this channel bottom. That's going to slow down the velocities on the outside of the water. So as we get away from those sources of friction, we're going to have our maximum velocity in the center. However, if the slope becomes less steep, the channel is going to erode unevenly. Remember, there are no straight lines in nature. That's true for stream channels more than anything. There is not a single naturally occurring straight line stream. So once we get the first bend, we are eroding the side of one of these channel sides. We're going to shift where that maximum velocity is. So we're eroding on that one side. We're removing material from the one channel slope. Now, as we move downstream, we're going to deposit that stuff on somewhere else. So what we frequently get when we have meandering streams is we have a cut bank and we have a point bar. So cut banks are areas of erosion. Point bars are areas of deposition. Cut banks were removing material. Point bars were depositing and placing material. So you'll see this pattern in pretty much every meandering stream. We could go to White Clay Creek just off of North Campus, where am I going? This way. If we go to White Clay Creek, we can see these point bars and we can see these cut banks pretty easily. So at every point bar on the opposite side is going to be a cut bank and vice versa. Point bars, because we have this area of deposition, that indicates that we have a lower velocity, low energy. That's where we can get stuff to settle out. If we have higher velocity, we're going to be cutting stuff away. We're going to be bringing up more material in. So this is all defined by the velocity and energy that's behind these channels. So as we saw with that image of the Amazon, we can eventually get a point where it's just a lot quicker for the water to jump the distance. Say during a flood event, we may, if we have this portion of the Mississippi with this massive meander, let's say we get a flood, we increase the water volume. All the water in the channel is going to rise. It's going to spill over that little land strip right there into the next part of the channel. It's going to erode away at that land strip until we eventually get to the point where all the water is going to preferentially flow and avoid this entire meander. So that's how we get what's known as oxbow lakes. These will stay filled with water for a while until eventually they'll dry out without any sediment supply and water supply. So these can be mapped out. These can eventually, over geologic time, we can map these out and find these in geologic formations. So they're pretty cool to find. They have really interesting features. So we can use these, our knowledge of meanders, to understand where to build things. So even though most people like to build along rivers because number one, it's picturesque. You have a nice babbling brook to fall asleep at night to. But if you build on the cut bank, as you can imagine, it's going to keep cutting no matter what you build on top of it. And anything you build on top of it is eventually going to fall if you keep undercutting the soil that it's built on. So during high flood events, high volume flow events, you're going to get even more cutting, and eventually you can undermine the entire foundation of a house if you're built on a cut bank. However, if you build on a depositional bar, you're probably a little more safe. You're not going to have to worry about erosion at those points. You're going to have nothing but deposition. You may actually have a problem with deposition at some point, which is an interesting problem to have. But so we're still in our zone 2, our transport zones. This is where we get floodplains as well. When we have these stream meanders, we have all of this really flat, elongated space surrounding it. So if you'll notice, the stream meander never goes any wider than the actual floodplain. So the stream meanders are going to impact the size of the floodplain itself. So whenever we have these high volume water flows, this can create what's known as an overbank flow, where the water level of the channel goes and exceeds the actual height of the channel. We're going to overflow onto the outsides of the channel. Since we're carrying that suspended load, all that silt, all that clay, the real small stuff that we can't see, once it's out of the channel, it's suddenly now in a low energy environment. So all of that clay, all that silt is going to settle out as the water infiltrates. And so we get these large floodplain deposits of this real fine-grained sediment that ends up being really good for soil development. So because of that, whenever we have floodplains, because they're so flat, because they're the soil is so fertile, they're really good for farmland. So a lot of farms will preferentially build and cultivate on these floodplains. Number one, it's flat. You don't have to level anything out. Number two, the soil's so good that creates really good crop yields. Also, the valley walls of the greater floodplain valley are going to create these natural levees that are going to help protect from any floods that come from the overland. So they're really, it makes sense as to why we build farmlands around floodplains. Okay, so this is a time lapse of Sacramento. And this is the farmland outside of Sacramento. Now, this is over, how many years is this? Actually, this is 20 years. No, 30 years, actually. So why do we not see any stream meandering in this area at all? What's up? What do you think? You think it's C? Tightly controlled by human intervention? What's indicative of human intervention here? Oh no, the answer is C. I'm sorry, that was pretty misleading. But what's showing you that there's human intervention?
Well, you can see how the land or the river is constantly.
Exactly. All of those parcels are farmland. They're all growing different crops. So whenever something that farmers like when it comes to land development is stability. So as you can imagine, a river meandering into your farmland is going to limit the amount of corn that you can grow. So they want that river to stay in the same place. So human intervention is what's dominating here. All those farmers have come together to keep the river from moving at all. Okay, let's take a quick 10-minute break and we'll come back and we'll talk about braided rivers. All right. Okay. So we were talking about stream channels and meandering streams. Those are instances where we have one stream channel, and that's the only thing that's meandering. But there are certain cases where we can get a different type of channel pattern, which is known as braided rivers. So we can get these river systems where there are multiple channels all in the same greater channel area, and they flow in different directions, but they intertwine at different areas. So from space, it kind of looks like braided hair. So these are pretty common in very very low gradient areas, very low energy areas. But we also have to have a couple of other characteristics in these cases. So for something to be braided, we have to have a very wide area and a very shallow depth. These braided rivers are probably no deeper than at least a foot, no deeper than a foot, maybe even 8 inches, 9 inches. So not deep at all. But these happen whenever we have a greater sediment load than what the stream can actually carry. So whenever the stream can't carry that stuff, it has to drop it out and deposit it. So that's why we get all of these huge sand and gravel bars, all of that heavy stuff, the sands and the gravels, the largest grain sizes in the sediment. That's going to be dropped out, deposited in all these bars. And since we have all of these different bars dividing the channel, it gives the impression that it's all of these different channels dissecting and intertwining with each other. So it's all the same water, it's just being diverted through its own deposition. As it drops more stuff out of its load, it's going to kind of diverge around those bars, those coarse gravel bars, and eventually it'll come back on the other side of the bar. But because there are so many gravel and sand bars, it looks like there's all these different channels coming about and intertwining and stuff. So we sometimes get these in these low energy environments. These are really common up in the plain of, like, outside the Rocky Mountains of Colorado. These are really common in Alaska, up in northern Canada. They get a lot of those because that's where we get the most coarse stuff. If you have a lot of coarse gravel and coarse sand, it's because you're closer to the headwaters. But you still have enough low energy where you can deposit it all out onto these plains. Speaking of deposition, now we're going to talk about zone 3. This is where we reach the end of the river channel. We're going to take all of that sediment that we moved from the headwaters, and we're going to drop it out of the river channel, and we're going to create these formations known as deltas. So you've probably heard of deltas. At the mouth of most of these rivers, there's a delta. It's just the buildup of all of these different sediments that have been carried by the stream. So this is where we finally drop out our ions. This is where we drop out that suspended load, the clay, the silt, those real fine grained stuff. That's where it's going to drop out, deposit into these long linear bars of silt and clay. So we're at our lowest elevation for the entire stream channel because we're at the mouth of the river. Because we're at our lowest elevation, we are at our slowest water velocity. We're not moving very fast. And since we have that low energy environment, that's how we're going to drop out all that suspended load. We need a very, very low energy environment to drop out clay and silt from suspension. So deltas, we get deltas at any point where a river meets a larger body of water, like an ocean or a lake. So this is the Nile River Delta. The Nile River Delta did not always look like that. There wasn't always this curve that goes up into the Mediterranean. The mouth of the river used to be much further south. And as you can see, Egypt is, for the most part, pretty dry, not very humid. But along the length of the river, it's all green. And then as you get closer to the mouth of the river, you're getting a lot better quality of soil. So that's where a lot of Egypt's since the dawn of Egyptian civilization, back when they were building the pyramids, that's where they were farming, and that's still where they're farming today, right on the Nile Delta. Such really good soil, and there's a lot of it built up. So that's why we tend to build farmlands on these deltas. Oh, okay. Okay, so this is the Mississippi River Delta as it comes out near New Orleans. So we have a wider stream flow. We're going to slow down those stream velocities. We're going to lower our gradients. And so we're just going to constantly build up sediment. So because we're going to keep building up all of this sediment, just like with what we had with braided rivers, as we're building up sediment, the stream is going to flow in different directions around those buildups of sediment. Remember, it's a fluid, takes the path of least resistance. So the Mississippi Delta has been changing a lot throughout time. So it didn't always look like the way it does now with that L of the lower part of Louisiana. So if we look at this graph, we have letters from A to G. That's what it looked like. For example, A, that blue one to the left, when those were deposited over 5,000 years ago, that's where the channel ended up, and that's where that delta started to build up. As that got built up, the channel started to preferentially flow a little bit up to the north. So we get B building up over here. Then we have C flowing around that delta down here. So as we get all these built up deposits of silt and clay, the stream is going to say, oh no, this is too much stuff in the way. I'm going to flow in a different direction, basically. So it's going to preferentially flow around those blockages that it creates with all the deposits that it's dropping out. And then those deposits are going to erode from wave action. If there's less wave action, they're going to build up. So those shapes that this image is creating, that's what those deposits originally looked like. As you can see, since it's on the coastline and we have all that wave action, it broke down those deposits into those just strips that you see today. So as you can see with G, this one small one right here, we still have a lot of it left because it's the youngest, hasn't had enough time to erode. So these deltas are going to continue to change over time, continue to build up land right at the mouth of the river. All right, so just some review. We have a river system from top to bottom, A, B, and C. Which portion of the river has the highest gradient? Shout it out, A, B, or C? A. Everyone agree? All right, that's right. A is the right answer. We have the steepest slope. Slope is another term for gradient. We have the steepest channel walls. So we're going to have the highest velocities. All of that stuff adds up to the highest gradient. Which portion of the channel is going to have the greatest rate of deposition? Remember, erosion is removing stuff. Deposition is dropping stuff off. Is it A, B, or C? C. Very good. It is C. That's where we have our lowest energy, lowest gradient, shallow channel walls, very low energy. So we're going to be able to drop all that stuff out of suspension. Remember, 90% of the sediment that's transported is the stuff that's in suspension, the stuff that's muddying the water. So that's going to be the biggest portion. Tell you what, we're going to introduce this quick, but we're going to go over this again tomorrow. So now we know how river systems work and how they change over time. Now we're going to actually quantify those characteristics. So we know the velocity of a river. We can measure the area of a river. We want to measure how much water that river is moving. So if we know the water velocity, we know a period of time for that velocity, and we have the cross section, which is the width of the river and the depth of the river, we can tell the discharge, or Q. Q is always going to be discharge whenever we're talking about hydrology. We can tell the discharge of the river. Discharge is just what's the hydrologic output? How much water is going to flow out of the river in a given time. So discharge is just a volume of water per unit time. So if we have a velocity, a cross section, and a time, what are our units going to be? What do you guys think? Feet cubed per second. Very good. So remember, we're talking about how much water. So we want to know the volume. And because we know the cross-sectional area and the velocity is a distance per unit time. So feet per second is a velocity. If we're multiplying that by the area is the feet by feet, so cubic feet. If we multiply cubic feet by feet per second, we're going to get cubic feet per second. Does that math make sense to everybody? Okay, because we're going to be working a lot with units in this portion of talking about flooding, because whenever we are measuring stuff, discharge is going to be really important. So the first step to measuring and calculating discharge is we're going to measure the stage of the river. The stage is just going to be the height of the water channel. And as you can imagine, the height of the water channel is going to be different as you go along different parts of the stream channel. If we're at the headwaters, we're going to have a much different height compared to the larger channel once we get to that depositional and transport zone. We're going to have a lot more water built up because we're getting a lot more water from tributaries. So that water is going to rise, the water level is going to rise based on how much water it's receiving from the catchment area. So we're going to measure the height of the river. Then we're going to measure the width of the river. That's from bank to bank. And we can do that through just measuring it or by surveying it. Surveying is probably the preferred way, a lot more accurate. So that's going to give us an area. The width times the stage, it's just feet by feet, that's area. Now we're going to measure the velocity. So there's a really simple way to measure velocity that some geologists do, just to get, if they just want a rough estimate. You measure out a meter, you throw a stick a meter in front of you, you count how long it takes to get to you, and that's your velocity in meters per second. So it's pretty rough, but most people have found that it gets you pretty close and can get you a better idea. Now remember, our fastest velocities are going to be at the channel center. So we stand in the exact center of the channel, and of course we want to stand downstream and throw it upstream. We don't want to be blocking anything whenever we're doing that measurement. But a better way to do this is using this flow meter. This is just a series of cones on a spinning axis on a stick that you're going to stick into the water. And what you're going to do is you're going to measure out these different distances along the channel. You're going to take a stream measurement, a velocity measurement, and it's going to spin based on how much water is moving past it. So it's much like the speedometer on your car. It's going to give you an output for velocity. So you're going to do that on each different stage along the river channel. You're going to average that out, and that's going to give you a more accurate velocity for the stream. So let's try this. Let's see what happens. So we have stream discharge. We have the average width is going to be 20 feet from stream bank to stream bank. Average stage is going to be 5 feet. And our average velocity that we found with our meter is 0.5 feet per second. So what is our discharge? Is it what? I can't hear what you're saying. B, is it 50 feet per second? Let's find out. It is B. Very good. Yeah, so how did you get that answer? That's exactly right. It makes perfect sense. 20 times 5 is 100. And if you half that with the 0.5, that's 50 feet. So very good. Okay, so this is a hydrograph of White Clay Creek right at Newark. The USGS, one of their first actual jobs, one of the biggest projects they've ever undertaken is implementing stream monitoring programs. So you can go to pretty much anywhere in the country and you will find a USGS gauging station that is measuring stage, discharge, water temperature, all sorts of stuff. There's a really good tool through USGS where it has mapped out every stream channel in the United States. You can pick a point on that stream, anywhere, any stream in the country, and it will create a catchment area for that exact point. So you can tell how much water is going to roughly be transported through that point. So it's really cool. I used that a lot when I was working on a water production job in central Pennsylvania. I used to be an environmental consultant, so I would do a lot of water studies, do a lot of well drilling to get production wells for large companies. One company in particular, they're a chicken manufacturer. So everything from raising the eggs all the way to slaughtering the chicken, they do everything themselves. They needed 1 million gallons of water a day for their new production of chicken. They were opening a new plant. They were gonna become the next Tyson Foods. They needed 1 million gallons of water a day. So we had to find 1 million gallons of water a day in central Pennsylvania, where the Amish live. And as you can imagine, the Amish do not like when you mess with their water. So it was a very interesting project to work on. We did a lot of these types of studies where we were measuring stream influx. We were measuring what would happen if we pumped the groundwater, because as you can imagine, as you pump the groundwater, the stream is going to start to infiltrate into the ground because you've lowered the water table. So water flows downhill. And if you've increased the gradient between the stream channel and the groundwater water table, it's going to flow downward into the water table. We're going to lessen the amount of water that comes out of that stream. So that was a really cool project to work on. We're pumping water for 3 days straight. You have to camp out there and monitor it, measure it, take temperature, take samples. So sometimes geology is fun, sometimes it's not so fun. That was a fun time camping in central Pennsylvania where there isn't a single good restaurant anywhere. But this is what that data looks like. So if we calculate our discharge, and we're able to calculate it based on stage and our height and our width of our stream channel, we can calculate discharge for an entire period of time. And we can measure and graph that out and find different periods of influx and outflux in the stream channel itself. So we have minimum discharge for this specific station of 30.2 cubic feet per second. So we usually use CFS in the geologic community. In the American geologic community, we use CFS just because American geology is so complex in its measurements, specifically hydrogeology, because we use CFS. Everywhere else uses liters and metric system. So the math is a little easier, but also in American geology, we go from CFS to gallons per minute, because whenever we're talking to clients, most people can imagine a gallon of milk and holding a gallon of milk in their hand and imagining like 500 gallons of water moving somewhere in a minute. It's a lot easier to explain to the layman. So it's a pretty complex measuring system. Okay, so let's see if we can read this properly. So we have our discharge in cubic feet per second on our y-axis, our time on our x-axis. So if we want to know the discharge at this specific station on April 16th, what was it relatively? And you can round to the nearest number. What was that? C, 90 cubic feet per second? That's right. And keep in mind, this is a logarithmic scale. So we're getting closer and closer. We're going up by increments of 10 on this y-axis. So very good, 90 cubic feet per second. So one thing to keep in mind is as we're going to increase the discharge in a river, which is the volume per unit time, we're going to also influence the stage height of the river. As you can imagine, more volume means the water has to go somewhere, so it can only go up. So more volume of water means we're going to increase the stage height of the river. So if we just measure the stage height of the river, we're going to be able to tell whenever there was a flood event. So this is the same exact gauging station. This is from 1995, and we had a flood in 95. So the max was 17.13 feet. We had the bank full stage is 10 feet. Bank full means that's the top of the channel. That's the maximum capacity of water that the channel can have. The flood stage was 11.5 feet. So that means the flood was 1.5 feet over the bank full stage. So, so for this specific one, on this one on the y-axis, we're measuring gauge height. For this specific location, this is the max that it's ever seen. The bank full stage is 10, the flood stage is an 11.5. At this specific point, are we at a flood stage? Yes or no? Are we at a yes or no?
Yes.
Yes. Are we sure? What's the number at the top there? We're at 9.5 feet at our highest. Because this is obviously, we got an influx of water, most likely from a storm event. But we're only going from 6 feet to 9.5 feet. The bank full stage is 10 feet. The flood stage is 11.5 feet. So we're still not there yet, but we're close. And we can see that we were almost to the bank full at 9.5 feet. So this may help to illustrate that. So here we have a regular stream up top below flood stage. This is probably what it experiences most of the normal amount of time, where we have that water flowing normally. We have those natural levees on the side of the stream channel. The stream channel is in a relatively balanced state. Nothing's flooding over the stream channel. We get to bank full stage. That's where the top of the water matches the top of the channel itself. And then flood stage, that's the height at which water is overflowing into the side, out of the sides of the channel. So with each channel, we have these, you can see these like slight slopes on the exact sides of the channel. Those are known as natural levees because as you get those flood deposits, it builds up those silts and clays on the sides. So that kind of helps to dam it up. But that's where we measure our bank full stage from, the tops of those natural levees on the sides. Anything that goes over that, that's going to be at a flood stage. So whenever we're talking about floods, we want to talk about the flood discharge. That's the volume of water per unit time that we're measuring. And that's what's causing the height of the channel to go, height of the water to go above the height of the channel. And then we also want to keep in mind the peak discharge, which is the maximum recorded discharge, because that'll give us a lot of information about the flood itself. Okay, so how do we compare discharge and stream stage? Because as you can imagine, it's really hard for us to constantly be out there with a velocity meter all the time, making those measurements. But we can relate discharge to the stage, right? As we see, these have a very similar slope, right? One of these, this is the discharge on here on the left in cubic feet per second. On the right, we have the stage. This is just the height of the water. So we can actually calculate and back calculate the discharge from just knowing the stage of the water. So this enables us to make these calculations constantly. If we just have a meter out there that's recording the water level constantly, we can make those calculations a lot quicker in real time. So we don't have to be out there with a meter taking these measurements by hand. So that makes it a lot easier for us to record these and to calculate these so we can get a lot more data out there. And once we have a lot more data, we can do a lot more with it and understand a lot more with it. So stage is going to be directly proportional to discharge. That's going to be a really important takeaway. If we can measure stage, we can measure discharge really easily. Because the only other components are the cross-sectional area, which we already know, it's going to stay pretty stable, and the velocity, which we can back calculate as well. So that'll be pretty easy. Okay, so we're going to get into rating curves tomorrow. This is where we'll pick up. We'll review discharge and stuff like that, and we'll get into rating curves, which is how we actually relate discharge to gauge height. So have a great Thursday, everyone. Stay dry.